I will announce the device position estimation for multi-tablet virtual display system. Information sharing using a large display or tabletop display is useful in discussions such as meeting. However, they are expensive, large, difficult to carry, and restricted to their installation location, such as meeting room, making their use inconvenient. Therefore, we propose arranging multi-devices such as tablet and smartphones to virtually compose one multi-display. By using the multi-display, information can be shared even in a conference room that is not equipped with a large display. The main difficulty for a multi-display system is the control of the system screen are displayed for the devices. In the multi-display system, the server needs to determine which part of the system screen to display on which device, so it is necessary to know the relative position of each device. The position detection of a device is made difficult by moving the device, occluding the device from each other or any other objects, and sometimes displaying the same content for each device. HoloLamp, a multi-display system, uses a 3D RGB camera to detect the position of the device. Since depth camera is expensive, a multi-display system using a general monocular camera is desired. In a multi-display system, the server needs to update the screen displayed on each device when the device is moved. For this purpose, the server needs to identify the relative position and orientation of each device. To identify each device position, orientation, and the device each other, markers such as a QR code and the method of using the image feature of content displayed on the device have been proposed. In this method, the marker obstructs the content of the device, and the device cannot be identified when the same content is displayed. Therefore, we will compose a multi-display system using a general monocular camera. In addition, it detects the relative positions orientations with a simple digital watermarking method. The purpose of presentation is to propose and evaluate the device position and orientation estimation method and device identification method using simple digital watermarking. We aim to compose a large scheme by combining multiple devices by using a system server to discriminate the device from each other and determine their position. Each device is controlled by the server, and the server prepares a wide virtual screen to be displayed. Each device displays a partial screen that corresponds to the position its own device in the virtual screen through cooperative operation with the server. In such dynamic relative device position tracking multi-display system, device position acquisition becomes difficult. Therefore, we adopt a method of displaying a specific pattern on the device, taking an image with the external camera, identifying the device, and estimating its position using recognition technology. We propose improved usability by making the pattern invisible to humans. Our method is a digital watermarking method that makes the pattern invisible by adding a minimal chain necessary for device detection on the device display screen. By adding a pattern, we can achieve device position detection, orientation detection, and device identification. I will explain the general flow of the processing when device detection. First, the watermark embedding process is performed on the server. Then, display the watermark screen on the device, and then take a video with the camera. And finally, the watermark extraction process is performed on the server. To detect a device screen area in the capture image, watermark should be embedded at the edge of the screen. The pixel value of a change in the area and device photographed by the camera to connect it to the server. In an actual multi-display system, watermark will be embedded and extracted in real time. Here, we are investigating if watermark can be extracted from camera image when they are simply embedded in the content displayed on the device. The device placed on a plane. All devices are photographed by a camera connected to the server, and the content displayed on each device controlled using the capture image. In device orientation method, It is only necessary to know a portion of upper or lower side of the device capture video. So embedding watermark in upper half area the device screen. When identifying a multiple device, identifying the devices by a difference in embedding sequence. If embedding a watermark at a different timing for each device perform watermark extraction processing on the camera image, the number of device portion estimation will differ for each device. A color image with a device screen resolution of W times H is a set original image I, and the pixel value of the width N change in the edge area. And unlike the original watermark, we simply change it to differ pixel value when the edge of width invisible enough. Hereafter, this is called the pseudo watermark. The invariance of the embedding signal guarantee only the time axis orientation, so we try to detect the device using a difference between frames. However, two images that only differ in the screen edge area are displayed alternately in units of 3 frames because of the unsynchronization when displaying a shooting. The device is placed on a plane and the pseudo watermark video is played on the device. A camera connected to the server takes a picture from above. The frame rate is matched with the pseudo watermark video during shooting. The frame number of the photograph video is I and the photograph frame is FY. However, the same images are in the frame units of the display, and the processing is performed with 6 photograph frames as 1 unit. The absolute value of the difference for all 9 combinations must be calculated, in which for 1 frame is selected from each. We consider if the difference frame with the maximum sum of pixel values can clearly distinguish the device screen area and the device background area when the binarization processing is performed. The difference frame is set to dj and calculated by G equation 1. dj with the maximum sum of pixel value for each different frame. dj is the different frame to be detected. By binarizing a brightness value of the selected digit shoulder, we can expect to obtain a rectangular count aligned with embedded signal. We adapt auto binarization method to binarize a brightness value. The device area is specified by detected as a counter rectangle. If multiple counters are detected from a binary image, we use the G1 largest counter rectangle area. The device screen portion is detected by device portion estimation, and the orientation of the device is estimated. Unlike the method of embedding a pseudo watermark estimation device portion, the watermark is embedded in the entire upper half W times H half of the original image I. The embedded strength is delta, and per delta change over all pixel of B value of W times H half of I to create a watermark image. Watermarks are embedded for the B value of I because humans are typically insensitive to change in blue color. The original image and G image with the watermark embedded in the upper half of the original image and displayed alternately in 3 frame units. The watermark extraction method is like the estimation of device portion, and the device orientation can be estimated by detecting the upper half of the device in the photograph video. The long side of the device is defined as the device orientation, and the counterclockwise angle from the push of x-axis of the shooting screen is theta. I will explain about device identification. To identify the device in the photograph video, we consider using different embedding sequence utilize the difference in the number of device portion detection. Each device is identified by making a frequency of the embedded signal for different from each device. We identify the 2 devices as device 1 and device 2. On device 1, 2 types of pseudo watermarked image in which only the edge of area of I is changed or displayed alternately in units of 2 frames. On device 2, 2 types of pseudo watermark image are displayed alternately units of 3 frames. The device position is detected by obtaining the difference between the adjacent frames of the photograph video. This method uses a difference in embedded sequence. Unlike the estimation of the device position method, it simplifies the difference between the adjacent frames of the photograph video. The number of detections of device position for device 1 and device 2 differ in embedding sequence for each device. The device is identified based on difference in frequency of device position detection. In the device position estimation, we conducted an experiment using one device and measured device position accuracy. We also measured the estimation accuracy when the device in the shooting screen was rotated. In the device orientation estimation, we conducted an experiment using one device measure device orientation estimation accuracy. The measurement was performed by changing embedding strength delta, which is a trade-off relationship with the estimation accuracy. The larger the embedding strength, the easier it is for human to see, so it is desirable to estimate device orientation with small embedding strengths. In the experiment, the insensitive results are clearly visually to also include it. In device identification, we conducted an experiment using two devices and identified two devices. The same model of two devices were used. The devices were identified by measuring the number of device position detection for each two devices in capture video. The content displayed on device is the audio image I. The audio image displayed on tablet with a screen resolution of 1920 times 1200 and two types of image were prepared in which the edge of area was changed by with 3 pixels, where the pseudo watermarked images by alternately connecting 3 frames each. The watermark image is I dash image in which the edge of I is black is I dash B, and the image in which edge of area gray is I dash G. In the created pseudo watermarked video, 3 frames of I dash B are linked with 3 frames of I dash Z, and this frame sequence is repeated. In the experiment, we played a pseudo watermarked video created by a device placed on a plane. We took the picture from above with a camera connected to the server. The experiment environment is shown in a table. We measured the device position estimation accuracy when the device is shooting screen was rotated. The device angle is 0 degree when the device orientation is vertical to the shooting screen. The device angle of 45 degrees and 90 degrees are follows. The estimation accuracy of the device position was measured with 12 device angle patterns. In device orientation estimation, the watermarked image that detects the orientation of the device is generated by manipulating the pixel value of the B channel slightly at the upper half of the screen. The watermarked image I dash was created by changing the values of delta to 10, 20, 30, 40, 50. An image with a watermark of delta equals 30. A watermarked video was created by alternately connection original image and the watermarked image every 3 frames. Similar to the device position estimation, the video was played on device and took the picture with a camera. Similar to device position estimation, two types of pseudo watermark images, I-B and I-Z, were created by manipulating the pixel value of the edge area of the original image. Pseudo watermark video to discriminate device 1 and device 2 from each other were generated for each device. The shooting was performed under the same conditions as the device position estimation and device orientation estimation by playing each pseudo watermarked video on 2 devices. About the result and discussion. As before, I will explain in the order of device position estimation, device orientation estimation, and device identification. In the device position estimation, 12 patterns of device position estimation accuracy with different device angle was shown. In device orientation estimation, 5 patterns of device orientation estimation accuracy with different embedding strengths are shown. In device identification, the result of 2 device identification experiments are shown. The device portion was estimated in the recorded video. This is an example of drawing the estimated device portion in the recorded video frame FY. The estimated device skin portion is represented by a green frame. The device skin portion of the estimated frame was detected only when all 4 vertices of the estimated device skin rectangle area exist within a circle drawn with a radius of 10 pixels centered over the 4 vertices of the device screen. The estimation accuracy of the device portion throughout the whole video was about 0.96. Show the estimation accuracy of the device portion when device angle changes on the recorded video screen. The horizontal axis of the graph is device angle, and the vertical axis is the estimation accuracy. The estimation accuracy is high. However, the estimation accuracy of the device portion was slightly low when the device angle was 90 degrees, 265 degrees, and 270 degrees. We saw that the device area displayed on the shooting screen was related. However, it is smaller at the device angle of 90 degrees, 265 degrees, and 270 degrees than at the angle. While the estimation accuracy of the device portion decreases when the device angle of 90 degrees, 265 degrees, and 270 degrees to the shooting screen is currently unknown. The device orientation was estimated for the recorded video for device orientation estimation. We estimated the device orientation by estimating the portion at the top of each screen. This is an example of drawing the portion of the upper half of the estimated device screen, so the orientation of the can be estimated. Similar to device portion estimation, the upper half of the device screen portion of estimated frame was detected only when all 4 vertices of the estimated upper half of the device screen rectangle area exist within a circle drawn with a radius of 10 pixels centered over the 4 vertices of the upper half of the device screen. Show the estimation accuracy of device orientation for each embedded strength. The horizontal axis of the graph is the embedded strength, and the vertical axis is the estimation accuracy. Fortunately, the smaller the embedding strength is, the harder it is for a human to visually recognize it. However, when the embedding strength is 20 or less, the estimation accuracy of device orientation becomes 0. When the embedding strength is 30 or more, the estimation accuracy of device orientation improves significantly. This is the experimental result of device identification. Device identification was performed for the recorded video for device identification. This is an image of the position estimation result for device 1. The device without the green frame is device 2. Device 1 plays a pseudo-watermark video in which either B and either C are alternately linked by 2 frames, and device 2 plays a pseudo-watermark video in which either B and either C are alternately linked by 3 frames. The number of detections of device 1 and device 2's respective portion was measured. The number of detections of device portion per 50 frames is 29 for device 1 and 15 for device 2, making the number of detections of device 1's portion nearly twice that of device 2. We confirmed the device can identify by using a difference in number of detections of device 1 and device 2 portion. Finally, a summary and feature work. To properly estimate device portion orientation and identification in a multi-display system, we propose a device portion estimation method, orientation method, and a device identification method that uses digital watermarking. We confirmed that a regular web camera could detect pixel changes in device's screen. In future work, we will use a specific watermarking method to perform detection experiments in various environments and propose a device identification method that embeds a watermark at a different timing for each device. Thank you for listening.